Hi, Year 11. So, we are going to look today at the Big Bang Theory and evidence for it. And in particular, we're going to look at redshift. So, very quickly, I'm just going to do a wee recap of the Doppler effect, and it will be quick because that was what we learnt last day, but that was like a week ago. So, I just want to remind you about it, okay? So, if we have an object and it is emitting a wave, then we tend to draw the diagram like this. So it's as if we're looking down on the object, and like this is the line representing the first wave that was emitted, and this is the second one, and they're growing out from that source. And if you remember, the distance between these lines represents the wavelength of the wave, and that wavelength will correspond to the frequency of the wave, and depending on whether it's a sound wave or a light wave that we're talking about, then that's going to affect how we hear it or how we see it. Okay, now the interesting thing is what happens whenever our sound wave or light wave is moving. So this wee diagram shows a moving sound wave quite well. So you can tell here in this diagram that our source of wave, sound or light, is moving towards the right of the screen. Okay, now if you're standing at point A and this source of a, let's go with sound first of all, so this source of a sound is moving towards you, then do you see how, because it's moving and it's moved every time it emits a wave, all the wave fronts get bunched up and you end up receiving waves which are of a much shorter wavelength than were originally being emitted. So if that's a sound wave, that means you hear that as a higher pitch, right? If you're standing at B and this source is moving over to the right here, and the source sound is, or the sound source is moving away from you, then that means because you are receiving the waves all like with a longer wavelength than was originally emitted, then that means that you hear it at a much lower pitch. And if you remember back in that video, I played you the clip of the motorbike going past, because that displays that really well. As the motorbike was coming towards me, it was making a higher pitch noise, and as it was moving away, it was making a lower pitch noise. Now, that's all sound. Same thing happens with light, but with light, the wavelength corresponds to the color of the light. So we talked a little bit about that in that video about the visible spectrum. So red, orange, yellow, green, blue, indigo, violet, all coming together to make white light. Now, shorter wavelength light is the blue end of the spectrum, and longer wavelength light is at the red end of the spectrum. So let's go back to this. If you have a source that is emitting light, so say it's emitting white light, which is a mixture of everything, and you're standing at A and this source is moving towards you, then the light that you are receiving is light of a much shorter wavelength, and that's the blue end of the spectrum. So you will observe the light much bluer than it is actually being emitted because of this effect here, which is the Doppler effect. As well as that, if you're standing at B and this light source is moving away from you, the light waves that you receive are much longer wavelength than the light waves that were actually emitted. So that means you are seeing them much redder, and we would call that redshift. Okay, so the light that you receive is of a much longer wavelength than was originally being emitted, and you see it much redder because red is the longer end of the spectrum. So that is called redshift. Whenever we receive light and it is shifted towards the red end of the spectrum, that happens whenever light is moving away from us. Now, there's a couple of videos mentioned in your notes here, so this is page 36 by the way. There are a couple of videos, I will link those on the stream for us, okay? But I just want to talk a little bit about redshift and how it is actually used. So, if you remember in the lesson where we were looking at the experimental evidence, we mentioned these types of things here, and these are absorption spectra. So if you imagine the light that is being emitted from a star, okay, then you've got a big range of wavelengths being emitted, and all those wavelengths correspond to colours, which is why it looks like this. But the gases that are in the star end up absorbing some of the wavelengths of the light, and that's what these wee black lines here correspond to. So there we would call them absorption spectra. Yeah. Now, this is just an example, a random example I got from Google, but it's just to remind you about that before we look at what happens whenever we look at these absorption spectra from distant stars and distant galaxies. Okay, so let's have a wee look at that. Sorry, I keep jumping all around the screen on you here. Anyway, so this picture here is quite good. So see if we look at this one down here. So if you look at my mouse pointer on the screen, so this lab reference would, I suppose, correlate to what we would see if we were to look at the light coming from our sun. So they would have the same makeup of gases there. So remember, these black lines refer to absorption lines, so they're corresponding to different gases within the star that are absorbing some of the light that is getting emitted, right? So if you look here at this bottom one, this is what we know it looks like whenever we look at the light coming from a star. If we then look at a star within our galaxy, what scientists noticed was that they got this same pattern of absorption lines. So do you see how we've got like the two thick lines and then a bigger space, this one, and then this wee thinner one? Do you see how going from this bottom one to this one here, the lines are just shifted ever so slightly towards the red end of the spectrum? That must mean, because of the Doppler effect, that this star is moving away from us. And what is even more interesting is that whenever they did the same looking at further away stars, so looking at stars which are in different galaxies but close to us galaxies, do you see how they're more red shifted? So the same lines are shifted more towards this red end of the spectrum than the ones in the nearby star. Same again if they looked at a distant galaxy. So galaxies really, well, they're all really far away, but you know what I mean, even further away, those lines are shifted more towards that red end of the spectrum, and then even further away, they're even more red shifted. So all of this is evidence that everything is really moving away from each other. So everything, and no matter what direction they looked in, the same thing is happening. So everything is moving away from each other, and the fact that these further away ones are moving away, or they're more red shifted, that means they're moving away faster. Because if you think back to that Doppler effect diagram with the lines getting squashed up or spread out, if it's moving faster, they're going to get more spread out, and that relates to being more red shifted. Okay, so the further away things are, the faster they are moving away from us. And this is the first big bit of evidence for the Big Bang. And because everything is moving away, and as it gets further away it's moving away faster, that is a bit of evidence that if we were to go backwards, then originally everything must have come from this one point and be moving away. So say we're at this stage, we're still going like this. If we were to go back, it would all come to one point. Okay, so let's have a little look at our notes on this. So this is page 36, and I will link this for you as well. Okay, so when we look at light coming from our own galaxy, we see absorption spectra similar to what would be seen in the lab here on Earth, and that's lines corresponding to hydrogen and helium and some other elements, but those two are the big ones. But when we look at light coming from distant galaxies, we see the same types of patterns in the spectra, but all the lines have been shifted towards the red end of the spectrum. So that's what we were just looking at there. That implies that these galaxies must be moving away from us. If we look in all directions, we see the same thing. So in fact, the further away galaxies are, the more red shifted the light is, and that means they are moving away from us faster. This is evidence that the universe is expanding, as all galaxies appear to be moving away from each other. And you have a little diagram of that there, but that's why I wanted to show you the coloured one, because it is a bit more obvious on it. Okay, so you can see here that what have we got? The bottom one is for, the top one is for our sun, and then you can see these other stars from different galaxies, they're more red shifted. So this is the red end of the spectrum and this is the violet end. So you've got the same pattern of lines all shifted towards the red end of the spectrum. Now, exam questions tend to ask what are the two big bits of evidence for the Big Bang Theory? So one bit of evidence is redshift. You do also need to be able to explain that. The other big bit of evidence is this cosmic microwave background radiation. And again, I will link to this video here. I need you to watch it. Probably be more interesting than me, but watch me first. So basically, whenever scientists listen to random areas, they can hear this radiation. They can hear this stuff, and they don't have a source for it. So what they're saying is that it is, because of the wavelength that it is and all that it's like an echo, or I think it's described as an afterglow in this of the Big Bang. I'm just going to read through this here. Okay, there's a wee typo. In 1964, two American astrophysicists detected microwaves of wavelength 7.35 centimeters. They realized they weren't coming from Earth or the sun or any stars, change that please, close to us. They found that no matter where they looked in the sky, day or night, they were able to detect these waves. So they concluded that the waves were coming from the cosmos or the universe. It represented the signature of afterglow of the Big Bang 14 billion years ago. We call it cosmic microwave background radiation, CMBR, but in an exam, I don't think they give you marks for CMBR, so make sure you're able to rhyme off these words. And it can only be explained by the Big Bang Theory. So two bits of evidence for the Big Bang Theory: redshift, cosmic microwave background radiation. Okay. Now, I am going to try and find another video, like a more interesting video on the Big Bang Theory for you to watch as well. Okay. But I'll go through the notes, and I will try and be quick here. So, the Big Bang Theory. So, well, I suppose I have already, excuse me, said a little bit about it. That's really the theory, that if everything's moving away from each other now, then it must have come from one point, and that point is called a singularity. So the Big Bang Theory suggests that all matter and energy in the universe originated from a single point called a singularity about 14 billion years ago. So I have underlined these. Make sure you do as well. And there was a huge explosion called the Big Bang. Straight after that, there was a short period of rapid growth, and that was called inflation. I should probably have underlined that as well. So as the universe expanded, it cooled and became less dense. As it cooled, protons, neutrons and electrons were formed, eventually allowing nuclei to form, and after about 380,000 years, the first stars came into existence. Now, on the next page, there's a diagram of, well, not a diagram, but like a timeline nearly of all the events. You don't need to know it in extreme detail, but you do need to know that as the temperature cooled, all these different things were able to form, and you do need to know the order that they were able to form in. So let's have a little look at that. Okay, so here we go. So time begins, and again, I will try and find I know this isn't exciting, and this is stuff that can be really exciting to watch. So I will try and find a video that gives you like graphics and things for it, because that's going to be more interesting. But let's look through it. So the cosmos goes through a super fast inflation, expanding from the size of an atom to that of a grapefruit, and that would be in a tiny fraction of a second. 10 to the minus 43 of a second. Too small to even visualize. So, post-inflation, the universe is a seething hot soup, dramatic, of electrons, quarks and other particles. Then, where are we? We're still before 1 second here. A rapidly cooling cosmos permits quarks to clump into protons and neutrons. So you need to know that these are the first two big things to have formed, right? Then, still too hot to form into atoms, charged electrons and protons prevent light from shining. The universe is a super hot fog. Then, over 300,000 years, electrons combine with protons and neutrons to form atoms, mostly hydrogen and helium, and that light can finally shine. Then, where are we? We're at 1 billion years. Gravity makes hydrogen and helium gas coalesce to form the giant clouds that will become galaxies. smaller clumps of gas collapse to form the first stars. So this is starting to tie in with the stuff that we were learning about the life cycle of stars. It's all coming together. Then, as galaxies cluster together under gravity, the first stars die and spew heavy elements into space, and those will eventually turn into new stars and planets. Now, I know I've said this 50 times, but I am going to get hopefully a nice video on this for you to watch. Then, I hit my camera. The questions on page 39, I need you to do those today, and I think I'll leave it until tomorrow to give you a quiz on this stuff, and then that'll give you time to let the information go in, okay? And the quiz will be cumulative again, to make sure that we are continually going over all that stuff, because if you remember at the start of this I said this is a topic, yeah, it's a really interesting topic, but it's like information heavy and it's very wordy, and there's a lot of stuff that we need to be able to rhyme off, so we will keep continuing to practice recalling all that knowledge. Okay, I will see you tomorrow. Bye.